social channels. Okay. Nice. You ready?
Yes.
It's still broken, but that's okay. We'll fix it eventually.
Welcome, everybody. Dr. Daniel Barth here, and you're watching How Do You Know? Welcome to our 77th program this week, and brought to you as usual by the book Star Mentor. If you're a experienced astronomer and you're trying to reach out and teach others, or if you're a novice to astronomy and looking for a good self-teaching guide, Star Mentor is your pathway to the heavens. So let's go ahead and take a look. We are doing a two-part episode this week. This is part 2 of NASA's Moon to Mars strategy. A couple of weeks ago, NASA dropped this document on us and said, here's our blueprint. Senthil's joined us. Welcome, sir. Glad to see you. NASA said, here's our document, our overarching architectural pathway from the Earth to the Moon and then on to Mars. And we talked about the organizational, what this document reveals about the thinking of the folks at NASA, and how the science programs basically view the flippy floppy government. Now it's my party running it, now it's yours, nature of the federal government to be a real negative. And they try to insulate themselves from that, and who can blame them? But I thought it was a very interesting strategy to see this ideology perpetrating this entire document, that we must make sure that we are insulated from the shocks and bumps and natural oscillations of a democratically elected government. So that's kind of interesting. This week, we're going to take a look at the science goals for Moon to Mars. And when we're looking at the science goals, what's really fascinating to me, I'm looking at this, and a lot of the stuff is I'm saying, as a science fiction writer who I've written quite a number of books featuring people living in an emerging colonial civilization on the Moon and Mars. And when you think about these things, you think about stuff like, okay, what are the science goals? What are the transportation needed? What's the infrastructure needed? How is this going to work? How is it going to pay for itself? How's it going to be something that's valuable enough that somebody's going to create it, and then robust enough that it's going to become independent, much as Canada, Australia, the United States started out as colonial enterprises and became independent nations. So we're looking at these things. There's a lot of stuff in there. I said, sure, of course. There's stuff that surprised me. And I'm like, wow, that's really, yes, that's thinking ahead. There's a lot of pieces. We're all very excited If you're old like me, if you're old and gray and remember actual astronauts in space landing on the moon and stuff like that when you were young, this is 50 years ago, friends. If you remember that sort of thing, the astronauts had everyone's attention. It was very dramatic, even in the days of the space shuttle. When the space shuttle would go up and the astronauts were on it, and we would focus on the astronauts, but the astronauts are quite literally the very pointy tip of a mighty iceberg. Beneath those few people who get to ride into space are legions of folks. And not just engineers and scientists and math wizards, but also people like folks who keep the buildings running, who keep the lights on, who run the cafeterias, who clean, who build and make products, and even just supplies. People who sell large institutions like this, things like Kleenex toilet paper and soap. There's a whole infrastructure that goes into creating the capability at its very peak to send a handful of very lucky souls out into space and actually doing the exploring, which makes sense if you think about it. So let's go ahead and take a look at NASA's science goals and see what they're looking at here. I'm going to take this pretty much in the exact order that the NASA document does. Of course, there's links to that, and you can put in to any search engine, NASA Moon to Mars strategy document. You'll have to thread through because you'll get a lot of news about it before you'll actually find the link to it. But it's worth reading, and it's nicely done. It's well produced. It's in color. It's a lovely PDF that you can download for free, of course, because it's NASA, one of these taxpayer-funded institutions. So the first segment they came up with was lunar and planetary science. And you're going, well, of course, moon to Mars. The idea here is NASA has these overarching ideas with each of these categories. Their idea here is they say, look, the surfaces of planets like the moon and Mars have basically recorded in their surface the history of the evolving solar system. As rocks fall from space and strike the surfaces of planetary and lunar bodies, marking them, creating craters from microscopic to mighty oceans of lava. We look at this and we say, well, the regolith, as we refer to it, on the moon and Mars, the regolith, the outer crusty layer made up of rocks and things that are subject to not only meteorite bombardment, but any sort of weather, erosion, these sorts of forces. And these basically mean that the surfaces contain this record of all these bombardments, these changes that have happened to the moon and Mars, and in fact, to all the planets in the inner solar system over the last 4 to 5 billion years. We're also looking at the idea that large craters actually punch into the interior, and then the craters eject rock from deep within, many kilometers deep within the interiors of the moon and Mars, far deeper than we could go if we were to haul drilling equipment there. They also want to be searching for prebiotic chemistry. What is prebiotic chemistry? We've talked on this program often enough about biogenesis, autobiogenesis, and other such things. Does life evolve essentially sympathetically once the conditions are right, just as stars form and planets form if the conditions are right? So, excuse me. NASA is looking for prebiotic chemistry. One of the things they want to do here is they want to understand what they refer to as an impact chronology. I've taught for many years when my students would make models of the lunar surface in clay or in plaster or other media, and we look at it and we say, well, there's an impact chronology here. There's a history of this, and you can look, and one of the exercises my students do once we make our structures, we say, well, which is the youngest? Which are the youngest craters? Which are the medium-age craters? Which are the oldest craters? How can you tell? Give me evidence for that. Forgive me. What the students are looking for, of course, is which crater is on top of which. If you think of it like footprints in the mud or in the snow, the first footprint in the snow is pristine on a blank white field, but every other footprint that steps on top of it later must have come later in time. So if I have a footprint which is clear and undisturbed, it might be hard to tell exactly when it was laid down. If I see a second footprint impressed over the top, what I've got now is I can compare the relative ages and erosions of the two, and I can say the one on top must be younger. It had to have come later. And so we can look at this sort of an impact chronology. On the moon and on Mars, they're virtually undisturbed by plate tectonics. On the Earth, we have lots of volcanism. We have lava erupts out. We have areas where the crust is spreading and magma makes new crust. Forgive me, hay fever. We also have subduction zones where one crust plate dives beneath the other. And as it does this, it carries billions, millions of years of history away into the interior of the Earth where it'll be melted and destroyed. These tectonic forces which destroy the history of the Earth's crust in a relatively short period of time, on the moon and on Mars, we don't have these. The moon, of course, is effectively airless and waterless. There are no winds. There's no atmospheric current. There's no hydrosphere. There's no regular melting and thawing of liquid water. And so while water may be locked up in the geology of the crust, or it may be deposited in craters in the far north, basically the moon, the only erosion is rocks falling from space. Think about everything you learned about erosion. Oh, water runs downhill and it carries soil and it breaks up rocks. And think to yourself, okay, what if now there's no air, there's no water? The only force we can get to wear down the rock and break it down into anything resembling a soil is small rocks falling in from space and hitting the big ones and cracking them. You might have to, if you said, ooh, I'm going to put a bucket down on the surface of the moon or on Mars, I'm going to wait until a meteorite falls into it. As you might guess, you might be waiting a goodly time before your bucket had anything in it. So we want to look at these geologic processes. We also want to look at volatiles. When we see these ideas of volatiles in these sorts of documents, what we're looking here is gases and liquids. Water is a big one, but also ammonia, methane, carbon dioxide, nitrogen, anything that could freeze into an ice if it was very, very cold, exist as a liquid if the pressure was right, and exist as a vapor if, again, the circumstances were correct. Because volatiles are what chemistry depends upon. So we look at those, and water is the most important one. Going on from lunar physics, let's look at heliophysics, the physics of the sun. So when we're looking at the sun, one of the most important things we look at is what we call the solar wind. The sun, of course, it's not a giant ball of fire. Please don't let anybody say that. It's a ball of plasma. It's gases, primarily hydrogen, helium, which are heated so hot that the nuclei are stripped of their electrons and they're a free plasma. The solar plasma happens because deep inside in the core, we're actually having nuclear fusion reactions. Hydrogen molecules are getting put together under conditions of extreme heat and pressure. About 10 million degrees Celsius is kind of the minimum, and tremendous pressure. And they put these together, and the two hydrogens make a helium. Yes, Virginia, the process is more complex than that, but let's just go with that for now. So we get the the fusion process, very violent. It's releasing a tremendous amount of energy, both in terms of physical pressure as well as energy, radiation, light. This pressure from the fusion explosion keeps the sun expanded. Gravity wants to make it compress. And basically, if you think about how do we sample the interior of the sun? Can't land there, can't drill there, can't send a probe there to sample it. It's the sun. And so what do? You look at the stuff that the sun releases that come out. And we refer to that as solar wind. Solar wind's lots of stuff. Solar wind is radiation and particles. When you're talking about radiation, neutrinos, gamma rays, light, of course. If you're talking about particles, electrons, protons, and you can talk about helium nuclei, helium-3 and helium-4. And these heavier particles, there's lots of other stuff besides, but they all stream out from the sun. Problem? Most of the particles are magnetic. They're either positive or negative. And we're trying to observe these things sitting inside a giant magnetic bubble. That's the Earth's magnetic field. The same magnetic field which shields us from cosmic rays and keeps the nasty radiation of the solar wind away from us so we don't all die of skin cancer. That solar wind makes it, that basic magnetic shield makes it really hard to observe the solar wind. The moon has, for any intents and purposes, does Mars. You can reside there, put instruments there, and they record the solar wind. The nice thing about the moon, very slow rotation rate, spins around once every month, basically, so a 700-hour rotational period. So it takes just a couple of stations, so you can observe solar wind all the time. And when we look at this sort of thing, not only can we observe directly what's happening right now, but these heavy solar particles on the moon, they will land and actually embed themselves in rocks and dust in the regolith. We know that in the regolith on the moon, there is helium-3. Helium-3 is a precursor product for nuclear fusion, could be used as fusion fuel. And the helium-3 basically lands on the ground and sits there, and you can harvest the lunar rock, heat it up, drive off the helium-3, capture it, throw the rock back on the ground, and it basically acts like a recyclable sponge. This is fascinating stuff. So, all to do with the solar wind. We also want to understand space weather. And you're like, what's space weather? Well, the sun is constantly putting out a stream of particles and radiation, but as you might imagine, that's not very consistent. If you pay attention to science news, and you're more likely to if you're one of my audience, you've probably seen where in recent weeks we're at a heightened period of solar activity, and there have been solar storms, and we've gotten all sorts of nifty auroras here on Earth that have been visible over a very much wider area than is usual. And so we've got this thing, and you're like, what's space weather? Well, if you're not out in space, then you can't get an aurora because the charged radiation particles strike you directly, which is very bad. When we're seeing the aurora in the sky, basically what we're seeing, friends, is the Earth's protective magnetic field shielding us from all sorts of nasty radiation and charged particles that form space weather. The density, the speed, The intensity of flux of these sorts of particles all make up important aspects of space weather. If we were to have a group of astronauts traveling from the Earth to the moon or from the moon to Mars, and a large coronal mass ejection or other solar event sent a bolide of radiation towards this vehicle, it could be disastrous. So we need to understand how these things not only affect our machines, our systems, our computers, and our health. So when we're looking at that, the other fun thing is that if we want to study the sun's magnetosphere, the sun's magnetic tail and its magnetosphere, which pulses, because hello, it's formed from basically a nuclear fireball. So of course it's a little chaotic. Again, if we're studying the sun's magnetic field, we can't really do that from inside the Earth's magnetic bubble. So going to the moon or to Mars allows us to access the sun's solar magnetic field in a pristine state. Moving on from there, we come into the human and biological sciences. If we think about this, we really know quite little about how space travel affects human beings. We are at the very infancy of that science. We have been putting people in space for some 50 or 60 years, and the total number of people who've traveled in orbit now numbers a few hundred. Well, we think about that, a few hundred people compared to all of humanity. Nah, we don't like those odds. We would rather have more test subjects, please. We would like to know more about it, please. And the total number of hours, of man hours spent in space travel is very small. So one of the things we're going to be doing, learning along the way, as real explorers have done for millennia. We will be boldly going, taking care of everything we know how to prepare for, but there are going to be some things which are going to be new, they're going to be different, they're going to trip us up. We're going to go, wow, this is a problem, I didn't know it would work like this. And we're going to be exploring, gathering data, and every group that goes out, the next group will be safer and more productive because that work gives us that much more experience. We also need to know how we're not going to go by ourselves. If we think about, let's go and stay on the moon long term, let's talk about a Martian colony, we have to think about plants and animals we're going to take with us. When we think about it now, it used to be on Earth, if we wanted to go colonize a remote island in the South Pacific in the 1700s, we would outfit a ship with sailors and botanists and marines and whatever else, and we would sail 8 months, 2 years to our remote island, and we would land on it. And the men would start a colony. Later, women would come, and this is how we would colonize an island. Well, the thing is, on Earth, all the biological essentials are there. We assume that wherever we're going, where there's going to be local flora and fauna, animals we can hunt and use for food, plants we can use for both food and other resources. We're going to go there. We've got air to breathe, water to drink. You know what? When we're going to the moon and Mars, we don't have any of those advantages. We have to take everything with us. There's not even going to be soil. Soil is a wonderfully complex thing. Soil is not just broken up rocks. It's organic material in various states of decay. It's all sorts of bacteriological legions of species. There's small animals, worms, arthropods, mammals, fungi, just oodles of things. Very much more. The stuff we find, even though it's powdery and looks like you could plant a petunia in it on the surface of the moon and Mars, is not the same thing. So we need to understand that. NASA has a list 5 hazards of human spaceflight. Hooray. And I'm looking at these and I'm going, okay. And the first one is radiation. Yes, that one's bad. You can't hear it, see it, feel it, taste it. So radiation, and it messes with your DNA and it breaks down your cells. So radiation is bad. So yeah, we need to take a look at that. Isolation. Can human beings live in an isolated way? People have done and can. Training is really a good idea here. You need training. You need people who are psychologically and physically strong before you send them out. But yes, we can do that. Distance from Earth. NASA puts this as one of the 5, distance from Earth. Do you think the people on the moon or on a science station, long-term science station on Mars, will feel more isolated than, say, the sailors of Captain Cook and other explorers felt in the 15, 16, 1700s, the age of exploration, when they're sometimes setting out for a 3 to 5 year voyage and they're a year and a half out, they're 2 years out and reaching their destination. Do you think the people on Mars or the people on the moon will be any more isolated? I don't think they will be. I don't think distance from Earth. I don't think just a distance thing. I don't think that's going to be a problem. I don't know. They'll worry about it and spend money on it. We'll see what happens. Variable gravitation. This one, yes, it turns out, gee, surprise, says human beings have evolved to live and thrive here on the surface of the Earth. We're pretty much adapted to live at normal 1 atmosphere of pressure, relatively moderate relative humidity, temperatures that are modest, and et cetera, et cetera. We're really, and gee, what other thing? Oh, yes, gravity. We and every other creature that shares the surface of the planet with us, we have evolved under 1g of gravitation. We've evolved under 1g. Because we've evolved under 1g, well, our bones, the way our blood flow, the way the musculature, arteries and veins work, our lymphatic system, the way our musculature is designed to carry food from our mouth down to our stomach, through our esophagus, all these things are designed around 1g. Turns out low gravity is not that good for you. We have strong evidence that certainly microgravity is seriously problematic. How bad the effects would be of lunar or Martian gravity. Remember, lunar gravity is about 1/6. So if we think about that, a 180 pound astronaut would weigh just 30 pounds on the moon. On the other hand, Mars is approximately 1/3 Earth gravity. And so if you talk about, again, your 180 pound person, now you're going to weigh 60 pounds effectively on Mars. If you step on a spring scale, calibrated on Earth, the 180 pound person will weigh 60 pounds. What it amounts to is there's not as much gravity pulling you down, but there's just as much inertia. It's a kind of a strange situation, but variable gravity does represent a challenge. And then hostile and confined environments. A hostile environment. When you're living inside of a machine for a couple of years at a time, think about living inside your current automobile. Is it in good shape? Would you be able to travel in it for 2 years without having mechanical repairs? And what if the environment outside was lethal? So crack the window, you die. The seal between the frame of the door and your cabin of your car breaks down, you die. So this hostile and confined environment, both the psychological confinement and the nature of living inside a machine that you must keep working at 100%. And if the efficiency of the machine falls off in any area, well, one efficiency starts to impact another. And pretty soon you're endangering your health and safety. So, yeah, those are NASA's big five. And one of the things they want to do is they need more data, so they need to evaluate crew health and performance. So these folks who are going through are going to be doing blood draws and blood pressure, and here, swallow this capsule. It has a telemetric data monitor inside of it. And we need to see you for some more tissue samples. Hooray! We need to sample your DNA again. Hooray! They're going to be giving up bits and pieces of themselves all during the journey and for a long time to come. The other thing we're going to be doing is, at some point, we're going to be taking some livestock with us. It'll probably start small. It'll probably start out with things like mold and fungi. It will probably progress from there to colonial insects, things like ants and bees. Then we'll start looking at larger livestock, preferably things like rats and chickens that can eat everything we throw away. I think it'll be a while before we see Angus beef on the moon, much less Mars. But we're going to have to take these organic ambassadors with us, because without them, we won't be able to prepare soil for plants to grow. So if we want to prepare soil on Mars, one of the ways to do that, we get a sample return, we find out what the regolith is like, and then we can make up a synthetic batch of Martian regolith in much larger quantities, thank you, and then say, okay, what do we need to add to this stuff to make it possible for food crops to grow in it? And once we get the food crops that we think will work, then there's the matter of transporting those seed stocks of all kinds to the various science stations and making them at home. So it should be interesting. Looking at a new division, physics and physical science. One of the great things about both the moon and Mars, they offer, for fundamental research, they offer really nice environments, particularly the moon. Again, excuse me, friends. Now, if we look at the moon, we've got no native magnetic field. We've got, we can put ourselves a few meters underground, and we're very much shielded from cosmic rays and stray radiation. No local radio waves or microwave signals of any kind. So you're radio quiet. You've got all these lovely advantages. Plus, we're working in low gravity, and scientists and engineers can find ways to leverage that too. So one of the things we're looking at, astrophysics, radio, and infrared astronomy. Now, we all know James Webb Space Telescope, yay, the current big star, the big 10-meter monster that's out at one of the Lagrange points and gathering data. We've seen other infrared astronomy. Radio astronomy had its birth in the 1940s, early 1950s, late 40s. And radio astronomy has been done on Earth for a long time. But again, putting up listening posts in the radio quiet areas of the moon. Plus, you could put them in the lunar poles and get a view of the different part of the sky. That's far less often studied from Earth, because our poles are very inhospitable to equipment. On the moon, it's all pretty much the same, dry, airless. We want to be able to leverage these experiments to help us develop material science and everything to get us from the moon to Mars. We're also looking at science enabling technology. This is one of these things that I looked at And even as a science fiction writer, I'm like, this gave me some great ideas and insights. We're looking here at the idea that, of course, our scientists, our astronauts, our explorers don't exist in a vacuum. We all know that the scientists, the astronauts call back, Houston, we have a problem. And Gene Kranz gets on the phone and he says, failure is not an option. Yeah, we all know about that. We think, there must be 100 or so people there in the little center on Earth because we're watching a movie, and that's true, right? In reality, thousands and tens of thousands and hundreds of thousands of people from around the world and across our country work to make those missions possible with the lunar landings. And we're going to be looking at the same thing over again. A tremendous, tremendous legion of men and women working, doing science, doing engineering, doing basic testing. And then there's all the infrastructure. Like I said, if you're going to have an organization, it has a building, you need a building superintendent, you need a custodian, you're going to have a cafeteria for your workers, you need people to run that for you. You've got parking lots and attendants and the people who maintain, fill in the cracks in the parking lot. You've got all this infrastructure, and they all contribute to get the astronaut to the moon. Because without all this infrastructure, the astronaut eventually, it's the old story, for the want of a nail, the shoe is lost. Yeah, all it takes is one little piece on the chain, and you realize what a titanic success these orbital missions are. So there's a whole lot of infrastructure that has to be developed here on Earth. And as we go to the moon, we will be taking our infrastructure with us. Yay! Like a child toting a creaky wagon behind him on a trip to the beach. We'll be taking all our infrastructure, clunking and heaving along with us. And some of the things we're looking at, science enabling, is also training the astronauts. So we're talking about one, mission-specific astronaut training. Each group of astronauts trains for a particular mission. We're going to go here, we're going to do here these things, we're going to learn all about this stuff. And all of this mission-specific training has to be organized, planned, and executed. We're also talking about the Earth-based science support. When we send our astronaut, explorer, adventurer scientists out into the deeps of space, they are not the very best in their scientific fields. They are explorers with a diverse and wonderful set of skills. But when we talk about the cutting edge science, we don't really expect that the PhD cutting edge scientist who's developing a theory of, say, lunar geology or Martian plate tectonics, that they're going to be that astronaut. So a lot of the brain power is sequestered back here on Earth. Of course it is. And the astronauts have access to it. They know enough to take use of the information they get, but the big brain power is back here on Earth. We're also talking about those volatiles again. One of the things we want to do is we want to find a way to sample some of the volatiles. We want to go to the craters in the north and south pole of the moon, which have not seen sunlight for 5 billion years. And we want to sample the ices there at the bottom of the crater and bring them back securely to Earth. We want to sample volatiles from Mars, including atmospheric samples, ground, subground ice samples of various sorts. We want to bring these things back to the Earth to get an idea of the subsurface environments and specialty shielding environments like northern crater environments on both of these worlds. We're also going to be developing not just robotic technology, but Waldo technology. Friends, do you know what a Waldo is? These are amazing. If you're operating a Waldo, it's sometimes called telepresence. Where do you typically see these? One place you see them is in laboratories or power plants working with highly radioactive fuels or particles. And you have a set of robotic arms inside a chamber that can reach down and pluck and manipulate. And the scientists outside has a set of hands, gloves, if you will, with fingers, and they are manipulating the robot over a distance. The robot becomes essentially an extension of the scientist, or we say telepresence. And these machines can imagine, you've all seen the Boston Dynamics robot. Imagine a Boston Dynamic robot hooked in by radio to an astronaut who could then be manipulating the suit that he was in, and miles away, the robot could be going ahead and performing difficult or dangerous activities. These Waldos will be wonderful because not only do they bring the robustness and safety of robotic exploration, but they bring the on site active intelligence of the human explorer. Martian and lunar infrastructure, we want to be able to support a continuous human presence on the moon and Mars. Eventually, we want as much as possible of our needs to be derived from in situ materials and resources. In other words, we want to be living off the land. We want to go to the moon. We want to go to Mars. We want to find places to get our volatiles. Can we find oxygen? Can we find water? Can we find hydrogen for chemistry and for fuel? Can we find a carbon source on Mars? That would be CO2. On the moon, that's more difficult. And can we set up this sort of robust, not only industrial chemistry that we need to survive and thrive and for our special activities, but practical chemistry for our everyday needs? Among these needs we're looking at safe and plentiful power generation. We know how the Perseverance rover does it. They have a small thermonuclear generator device on the back end, and basically it's a piece of hot plutonium, and it gives off heat, and from the thermocouple, the heat is turned into electricity, and the electricity powers the rover. That's pretty darn cool. Could you scale up for a whole science facility? Wow, that's an interesting thought. Certainly, bringing in diesel fuel to run generators for electric heaters and infrastructure isn't an option. So we need to be looking at something. How much solar energy can we harvest? And how do we distribute this to the places where it's needed? We need to talk about communications architecture. We all fuss about it, don't we? We say, oh, my cell phone signal is bad. Oh, I can't get enough internet signal to surf the web and these sorts of things. Well, guess what? Data, voice, internet, those things that they advertise when they want you to switch phone carriers or cell providers. Yeah, data, voice, and internet. These infrastructures are going to have to be brought with us to the moon and Mars. We need a GPS-style navigation system. Will it be LPS and MPS, the lunar positioning and Martian positioning systems? Either way, you need some kind of basically satellite system for navigation. Neither the moon nor Mars has a magnetic field. That means getting a fix on where you are is more difficult. Not that it can't be done, but you need to have some fairly sophisticated stuff. Having a GPS system would make everything so much simpler because it would offload the navigation and we wouldn't have to pack it with us, just have a GPS receiver and a maps device like, oh yeah, one of these, right? Hey, Google, map the Mariners Valley for me, and I want a buggy route to go from this point to that point. One day, perhaps. We're also looking at manufacturing and construction. Hello, Captain Obvious. The moon and Mars are far, far away. Now, the moon, if you had a regular transport system to the moon, like Buzz Aldrin's Cycler, and perhaps we'll have a program on that, Buzz Aldrin envisioned a system where essentially a spacecraft would figure eight orbit around the Earth and the Moon, and basically it would be a transportation hub. You wanted to get from the Moon to the Earth. All you had to do was blast into orbit, catch the cycler, and then you are carried along to Earth, and then you drop off of the cycler and you descend and enter into the Earth orbit. And the whole navigation and transportation between the Earth and the Moon is handled because this spacecraft keeps going all the time. In any case, in the short term, we're going to basically need orbital fueling technology. Think about the refueling that military planes do when they're on long missions and they meet up with a tanker plane in midair. Well, you're going to have to do the same thing except in orbit. How do we routinely transport people and materials in bulk safely and cheaply from the Earth to the Moon and then from the Moon to Mars? We're also looking at transportation, habitation, and operations. Once we're on the Moon, how do we get around? How do we handle transporting supplies, equipment, results, products? At some point, we're going to want to be producing products and shipping them about to one place to the other. Surface to orbit technology has to be improved. We also need habitats. How do we have a habitat? What should it look like? Should it be some sort of inflatable thing like a bouncy house made with Kevlar, and we drop it down and it inflates and we open the door in the airlock and walk in and here it is and it's all inflated and it's ready to go? Are we going to go there and build it? We're going to live in the spaceship and go out every day to build our habitat and then move into it? Various models here that need to be tested. And of course, we need to make sure that everything is okie dokie between the equipment and the astronauts. There's going to have to be an entire infrastructure system that's just about monitoring what's going on with our habitats. How are they functioning? How well are they doing? It's going to be an important piece of the puzzle and something we're going to have to dig into. The nice thing is that once this gets going, it becomes a juggernaut of its own and it's not easily derailed. And once it becomes a financial juggernaut, then it employs lots and lots and lots of people. We may have 6 or 7 astronauts on a spacecraft at a time, but I can guarantee you there are more than 10,000 for every single astronaut that makes it to orbit. More than 10,000 people, probably closer to 50,000 people, have been working, laboring in some capacity to make this whole social mega project work. So that's where we're going to wrap up for today, friends. Paul, did we get any fun questions? There's our link for you in the For More Information section at the end of our weekly crib notes for our program. So there's a download there. You're welcome to contact me at astronomyforeducators@gmail.com. And if you have program suggestions or something you'd like to see on our show, we'd love to hear from you. And in any case, that's where we'll wrap up for today. So we wish you all a grand week. Clear skies. The weather's getting warm. If the skies are clear, get out there with your binocular telescope and reacquaint yourself with the skies now that winter's grip is gone. We'll see you all again next week, folks. Thank you very much. And remember, keep thinking about how do you know? Bye-bye.